You are watching a 10-part video series on location analytics. This series is presented by Michael Erskine to complement BIA 4100 Location Analytics at Middle Tennessee State University. Module 1. Recognizing Spatial Problems and Opportunities. By the end of this module, you will be able to explain what makes spatial problems special problems, define location analytics and geographic information systems, and describe fundamental concepts of spatial analyses. Take a guess as to what we're looking at in this image. Any ideas? Well, it's an image of cholera bacteria captured by a Zeiss electron microscope. Now you may be wondering, what does this image have to do with location analytics? To answer that question, let me share a true story from the 1850s. This image, aptly titled "A Court for King Cholera," captures life in the poorest sections of London in the 1850s, a time of multiple cholera outbreaks. During that time, scholars struggled with determining the exact source of the outbreaks until John Snow presented his findings. What John Snow did was rather simple. He plotted cholera deaths onto a map of London, then added other features such as water wells and pumps. Using these maps, John Snow was able to determine and convince others that a specific pump was responsible for the outbreaks. While there certainly were prior cases of location analytics in action, the John Snow maps are some of the earliest and well-documented examples of solving a problem using location analytics. Since then, location analytics has become even more powerful. As these headlines suggest, location analytics can reward investors, create corporate revenue sources, be fundamental to modern business models, and even revolutionize the world. If the John Snow example and these headlines can't convince you about the utility of location analytics, maybe some cool maps will. Take a close look at this map of commercial air traffic in the Middle East. It's easy to spot that the airport in Istanbul, shown here, is far busier than the airports in Tehran, here, or Baku. You can also see that there's a clear air traffic route through this region that avoids the Syrian and Iraqi airspace. And you can identify that there's a no-fly zone over Syria, as there is no commercial air traffic at all. Here we're looking at a nighttime satellite image showing light pollution. Can you take a guess as to what part of the globe we're looking at? Let me give you a hint. It's in Asia. Still not sure? We're looking at the Korean Peninsula. The light pollution of South Korea shows a clear difference between the light pollution in North Korea. So much so that you can practically trace the political border. Of course, light pollution can tell us a lot about the economic prosperity of a place, and therefore we can recognize the enormous economic difference between South and North Korea. Here's another fun image. At first glance, you probably recognize this as a map of the world. But if you look closely, you will notice that countries or continents are not shown at all. This map traces the movements of container ships in 2019. Therefore, what we're seeing is the global movement of goods. Hopefully, these examples gave you a taste of what's to come in this course. While there are many technologies available to perform location analytics, we will use just 3. Google My Maps, which requires a Google account or a Gmail account, QGIS, which is available for free via an open source download, and Carto, which is also available to you through the GitHub Student Developer Pack. There are a lot of reasons that location analytics and geospatial data is different than traditional data. Let me briefly highlight these. Geospatial data is multidimensional data, meaning that there are a minimum of 2 coordinates, x and y, or latitude and longitude. Geospatial data are almost always filled with large volumes of data. When working with satellite imagery, the resolution makes a difference, especially when visualizing. There's different representations which result in different analyses and, of course, different findings. Geospatial data often take real-world or 3-dimensional objects and try to project these on a flat surface. Geospatial data is examined using unique analytic methods. Unfortunately, these methods and analyses are time-consuming. And finally, updating data is far more challenging due to the number of different sources and the large file sizes. Take a look at this photograph of a sandbar in Mexico. You might be wondering, what does this sandbar have to do with location analytics? Surprisingly, location analytics transformed this sandbar into a global tourist destination. All of this happened in the 1960s when Acapulco was the place that most people would go when flying to Mexico. During that time, the Mexican government realized that new tourist destinations were driving away traffic and dollars from Acapulco. So they turned to location analytics for a solution. They wanted a location that had great beaches, great fishing, a large labor force, few mosquitoes, was less than 4 hours from most of the US population, and was less than 8 hours from Europe, plus many other parameters related to the weather, climate, legislation, and the oceans. Their computer system, an early geographic information system, recommended this sandbar. Mexico invested, and today the sandbar is Mexico's top tourist destination, Cancun. This photograph is of the hotel zone, with the lagoon in the top left and the Gulf of Mexico on the bottom and on the left. Since Jon Snow and the Cancun example are from years ago, you might be wondering, why study location analytics today? Well, the answer has to do with the mobile sensors we all carry in our pockets, cell phones, and the data they collect. For instance, this is a snapshot of a live Twitter data feed. Notice that the section I highlighted includes geographic coordinates. If you enter these coordinates into Google Maps, we can see where someone took a Halloween-themed photo of Alice in a spooky land. It's in a cornfield just outside of Lincoln, Nebraska. In the next section, I want to help answer the question, what are geographic information systems? The formal definition is GIS is a computer-based system to aid in the collection, maintenance, storage, analysis, output, and distribution of spatial and non-spatial data and information. Let's take a look at each of these keywords. A collection refers to the ability of a GIS to ingest many different types of information. In fact, using many different formats, many different types of data are one of the main functions and benefits of a GIS. Maintenance refers to the task of keeping the collected data up to date. The world is not a static place. Therefore, oftentimes, data collected about the world needs to be updated. A GIS can support dynamic data that changes often. The flexibility of a GIS to collect and maintain static and dynamic data is another strength of GIS. Storage refers to the structure, coding of information that is stored in the digital format. The data can be stored in a simple or complex structure. The GIS is well suited to collect, maintain, and store data sets ranging from in size from very small, such as a few kilobytes, all the way up to multiple terabytes and beyond. Analysis speaks to the analytic capabilities of a GIS. When a GIS analyzes the spatial information that has been collected, maintained, and stored within, it turns that data into information. Analysis techniques are from a wide range of fields and assist the user of a GIS by uncovering spatial patterns in the data. Output refers to the maps, reports, and statistics. Typically, the output of a GIS is a map. A map is a visual representation of the spatial phenomenon known as reality. Through the collection, maintenance, storage, and analysis of reality, a GIS can produce a visualization and model of the world. Distribution. GIS allows for easy sharing of spatial and non-spatial data and information around the world in both visual and tabular, that's tables, formats. You've heard me mention spatial and non-spatial data a few times. Spatial and non-spatial refers to the capability of a GIS to hold information whether it has a spatial component or not. Let's consider the 6 parts of a GIS, including hardware, software, data, methods, people, and the network. Hardware is perhaps the simplest part of a GIS to explain. The hardware parts of a GIS refer to the powerful computers, output devices, monitors, input devices, disk space to store the large GIS datasets. Typically, GIS computer workstations are quite powerful. However, more recently, we've seen GIS workstations move to the cloud. Now, software is at the heart of the GIS. The software refers to the many free and commercial software packages that allow GIS users to perform functions such as the manipulation, storage, query, and analysis of spatial and non-spatial information. Data storage is critical to the GIS. Any and all spatial and non-spatial information is stored in a digital format on the computer or in the cloud. A GIS can ingest just about any type of data in a wide variety of formats. The ability for a GIS to be able to consume this range of data without degrading the performance or having any data overload issues is essential. With the wide proliferation of sensors we have today, like the cell phone in your pocket, the GIS can determine what to do with this large amount of data. It's often difficult for a person to understand what's even inside these data sets. However, a GIS can visualize the data as a map or graph and helps humans understand and weed through these massive amounts of data. Now, GIS uses a variety of analytic methods. These methods refer to the formulas, statistics, analyses, and algorithms that are used to turn data into information, so that humans can turn that information into knowledge through interpretation. People are another essential part of the GIS. People refers to anyone that uses a GIS. This includes the general public that may be looking at a printed map or a digital globe, all the way to skilled GIS professionals that build new functionality and push the limits of what is possible. People can also include geospatial professionals, data scientists, software developers, policymakers, and citizens. The final part of the GIS is the network. Networks refer to the computer and the social network. Both of these networks assist in the dissemination of data. Whether the dissemination of data occurs through transferring data sets or collaboration, sharing the data from a GIS is a very common and useful operation. Additionally, these networks allow for the display of information on the form of web maps, web applications, or even paper maps using our social networks. How can you use location analytics? While the use of location analytics in business is still relatively new, various areas have used GIS and location analytics heavily, including logistics and supply chain, the military, agriculture, wildlife and disaster management, utilities, decision support, healthcare, and mining. Before you start your journey down the path of location analysis, it's important that we cover a few fundamental concepts related to space. An understanding of how space is represented and measured will provide an important foundation for you to build upon. Space, location, and distance are fundamental concepts of spatial analysis. Space can be measured in absolute, relative, and cognitive terms. Absolute space can be thought of as mathematical space. Absolute space involves the precise measurement of location in space, such as XYZ coordinates. Absolute space should provide an unambiguous description of space. For example, all the information coded on the topographic map shown here is stored and displayed as a representation of absolute location in space. All locations and features are all described using precise measurements and calculations. Space can also be measured in relative terms. Relative space deals with the definition of one location based on the location of another object. A subway map is a great example of this. Relative space deals with the definition of one location based on the location of another object. These topological relationships represent connectivity between features of the world. In topological space, precise measurement of space is not as important as the relative description of spatial features. For example, in this New York City subway diagram, the map shows all routes. Note that each stop is pretty much evenly spaced. Do you think this would be true in the real world? No, of course not. As a rider of the New York subway, you're not concerned with how far apart the stops are, but instead how many stops you need to go before you get off the train. Space can also be measured in cognitive terms. Cognitive space reflects people's beliefs, experiences, and perceptions about places. For example, this is a drawing of a university campus from a student's memory. A freshman student may know the exact location of the dorms, the student union, the dining halls, but not know the rest of the campus at all. Conversely, a senior who lives off campus may know the location of every parking lot really well, even the location of many classrooms, but may not be familiar with the locations of any of the dorms. Location is another fundamental concept of spatial analysis. Location can be described in 4 ways: absolute, relative, cognitive, and nominal. Absolute location is considered an unambiguous descriptor of the location, typically expressed as a coordinate, such as a latitude and a longitude. An absolute location cannot be confused with any other location on Earth. Location can also be described as relative. Relative location is expressed as both the concept of the site and the situation. For example, physical attributes such as the city or the ocean, or the situation such as being 80 miles away from Atlanta. Location can also be described in cognitive terms. Cognitive location refers to the personal cognitive image of places and regions compiled from personal knowledge and experiences and impressions. These are two images of Nashville. The top image is most likely of a bachelorette party, and the bottom image is of the Grand Ole Opry. Depending on the visit to Nashville, the person may have memory of one or the other situations, and that will form their memory, their cognitive memory of the location. Perhaps the most interesting concept is the idea of nominal location. A nominal location is a location that you remember being at when you heard about an event that took place at a very different location. Therefore, the location where they heard the news is the nominal location, which is linked to a distant location. For example, if you were around during the World Trade Center attacks in 2001, you probably know exactly where you were when the attacks occurred. You may also remember where you were during another major event, such as the Super Bowl. It's important to remember that unlike absolute location, relative, cognitive, and nominal locations are all determined by our cultural systems. Each culture will have influence on the way we describe and perceive space. Distance is the third fundamental concept of spatial analysis. Distance can be described in four ways: absolute, relative, and cognitive. Absolute distance is a physical unit of measure. For instance, the number of miles between downtown Houston and downtown Toronto. Or this image, how many miles to Bowling Green? Distance can also be measured in relative terms. For example, you could consider other metrics such as the time needed, the effort, or in the case of tolls, the cost to travel somewhere. Finally, distance can be described in cognitive terms. Cognitive distance refers to an individual's perception of how far things are apart. Consider the trucker in the top picture. While you might consider driving to St. Louis or even Denver quite far, this would probably not be the case for the trucker, and even less for the airline pilot. Everything is related to everything else, but near things are more related to each other. This quote is a fundamental first law of geography, and the reason that location analytics is so powerful. This law speaks to the idea that space and relative and cognitive relationships featured in that space have an influence on the development and interaction of the features. Consider the concept of a friction of distance. The further you have to go, whether it's through cognitive space or physical space, the less likely you are to travel. For instance, you would rather buy a sandwich from the shop next door than from the shop across town. With that important thought, we'll end Module 1, Recognizing Spatial Problems and Opportunities. In this module, you should have learned to explain what makes spatial problems special problems, to define location analytics and geographic information systems, and to describe fundamental concepts of spatial analyses.